Okay, off we go. So, here's where we left off. So we were talking about higher order partials. We should have, ideally, some sort of geometric sense of what this looks like. Now, again, I remind you, I know you've heard me say this a lot, but what calculus looks like depends on what kind of a picture you're looking at, right? This is very, very important. Okay, so if you're looking at level sets, if you're looking at a parametric curve, if you're looking at whatever you might be looking at, the pictures of calculus, what geometric interpretation you make, is different depending on that context. So we are going to focus here on the graph picture. Right, so we're going to look at a picture of a function of two variables. There you go. We have a surface. It's a graph of a function of two variables. And we ask, what does a second partial look like on this picture? Okay, so, a couple of these are actually pretty straightforward. So let's think about, for example, fxx. Right, so that's the x partial of the x partial of f. And conveniently, we're taking the partial derivative with respect to the same variable twice. Which means that, the first thing we're going to do is we're going to hold y constant. And then we're going to continue to hold y constant, right? So for the purposes of this calculation, y is constant for the whole calculation. And here's kind of what that looks like if you hold y constant. Right, you're going to look at basically a cross-section perpendicular to the y-axis, which means that your graph, previously a surface, now is just a curve, right? And so what happens if you take the partial derivative with respect to x? Well, that's just second derivative in the x direction. And effectively, we only have a single variable here at this point, right? Y is a constant. It's not really a variable anymore. And in a single variable context, second derivative is a pretty well-established interpretation. It just speaks to concavity. So in particular, the fact that it is concave down means the second partial is negative. And vice versa. The second partial is negative. That means that cross-section is concave down. You can make an analogous argument to entertain the question of how would I interpret fyy. Of course, in this context, it is x that is constant. Right? So we're fixing and holding a single value of x. That means that the cross-section is now, again, a curve. But notice, the concavity does not have to be the same. Right? Now this is a sort of a new thing in multivariable calculus. There is no single variable version of this. Right? Brand new idea. Depending on which direction you're going in the domain, concavity will be different at the same point. Right? So again, brand new idea. And in this case, of course, you notice the concavity is upward, and that tracks with this partial being positive. Okay, all right. So that's again, pretty straightforward. A couple of little bumps in the road there, but basically the idea that you might have expected. Let's see here. Where it gets a little challenging is if you talk about mixed partials. And what's hard about this is I can't just say, of course, we're just looking at a single variable function here because one of these variables is constant. Because it isn't. When you take the y partial, x is constant. But when you take the x partial, x isn't constant any longer. Now x is an actual variable again. So, there's weird, different things happening at different stages of the calculation, and that really changes how we can approach this. We're not going to be able to take we're not going to be able to find a point of view that makes this basically kind of a lot like single variable calculus. This is substantially different. So here's what I'm going to do. I'm going to interpret the two different derivatives in question in different ways. We're going to understand the first partial that we take in terms of slopes of graphs. And then we're going to interpret the second partial, in this case the x partial. We're not going to interpret that in terms of graphs. We're going to interpret this in terms of a rate of change as you move in that direction. Okay, and you're going to see momentarily we kind of have to. Okay, so the picture. Let's see, I'm not going to be able to get all this on at the same time, so I'm going to have to shrink it a little bit. That ought to do it. Okay, so we are looking, presumably, at the graph of f. You'll notice I did not draw the surface that is the graph of f here. I tried. And the conclusion I came to is that the picture got more confusing with my attempt to draw that than it is without my attempt to draw that. So yeah, I think we're all best served here. If you just kind of use your imagination, imagine that there's some surface there, and what I've left drawn is the stuff that's immediately relevant to what we're actually calculating. So there's some sort of a surface there, graph of f, and looking at the graph of f, what is the y partial of f? Well, that just says as you go in the y direction, look at the tangent line to the surface, this surface that you're imagining, right, that I haven't drawn. But there will be some tangent line, again, in the y direction. Maybe it looks about like what I have highlighted in green there. So that slope is the y partial. And I can do this at various different points down here in the domain. Notice at all of these points I'm going in the y direction. But since I'm at different points, I will get different shaped tangent lines. Because, of course, the surface is different over there, and who knows what it's going to do. Okay, so the y partials are the slopes of those tangent lines to this, imaginary surface that I'm not going to draw. Okay, so what about the x partial? How do we understand the x partial here? And why don't I just draw the graph so that I can interpret the x partial as slopes of the graph? And here's the problem. I'm already looking at the graph of f. Right, we have a picture, again, in our minds, right? It's the graph of f. I'm not taking the x partial of f. Right? I'm taking the x partial of a different function. I'm taking the x partial of the partial of f with respect to y. And I don't have a picture of that. And I don't want to have to imagine a picture of that because then I'd have two different graphs and oh god, that'd be super confusing. So again, we're going to take this different interpretation. The way we're going to understand the x partial here is we're going to imagine how does the thing we're taking the x partial of change as I move in that x direction, right? So now the x direction is kind of coming out of the screen. So we're looking at y partials. The y partials are slopes in that direction. And I want to know how the slopes in that direction are changing as I go in that direction. Right? And so I'm going to attempt to use my hands to kind of describe what we're seeing here. I start off with slopes like this. Right? So that's a negative slope in the y direction, sort of in the bar back there. And as I come out of the page, right, as I go in that direction, those slopes, so watch my forearm here now, those slopes are kind of doing like that. Right? So they go from like this to like that. So, all right, well, what does that mean about the value of this x partial of this y partial? Well, these y partials are, let's see here. Oh gosh, let me just label the numbers. There, that looks like about -2 to me. And there, that looks like about -1 to me. And, oh gosh, there looks like about -0.5. And then here looks about 0. And then here, golly, I think that's starting to look positive at this point. Maybe it's about +0.5. And so now I ask, looking at these values, right, as I go in that x direction, check it out, those y partials appear to be increasing. And that means that the x partial of that y partial is positive. So what we have here is an example, right? Not that they all look exactly like this, but this is an example of how you can make sense out of what a mixed second partial looks like. And this is an example where the x partial of the y partial ends up being positive. And if you think about, again, this kind of thing here, it's almost like there's a sort of a twisting of the surface, right? That's just sort of one metaphor that you might find satisfying, perhaps. But anyway, in this case, it's sort of a twisting of the graph. Okay, it's very geometrically challenging, right, to see that, but that's kind of what it is. Okay, moving along. So let's see here. Let me get back into the full screen mode. Okay, so let's talk about section 3.1. You will notice that section 3.1 is a little bit out of order, right? We just finished 2.4. So why aren't we going into 2.5? And the reason why is there is a certain point of view on how to think about derivatives that I find particularly satisfying, that I've actually already made a reference to, but that I'm going to be using pretty heavily in section 2.5. And that point of view is covered very nicely in section 3.1. And so I just figure it's easy to just do 3.1 first, and that'll arm us fully to make use of that point of view in 2.5 when we get to it in a few minutes. So here we go. We're going to talk about parametric curves. You all remember parametric curves? Right? The idea of a parametric curve is you have position in space as a function of a single variable, typically time, and I'm going to go with time here as a very helpful and convenient choice. Okay, so position is a function of time. All right, we're going to talk about the derivative of such a function. There's several things to say about it. Let me remind you, when we look at this kind of a function, specifically understanding it as a parametric curve, geometrically, when you draw a picture of a parametric curve, you are not looking at the graph. Cannot emphasize this enough. You're not looking at the graph. So all of these ideas that you have about the calculus of graphs and how partial derivatives are slopes of tangent lines and stuff like that, out the window. Right? It doesn't have anything to say about what we're doing here, because here we're not looking at a graph. If we were looking at a graph, there would be a t-axis. There isn't a t-axis when you draw a parametric curve. Right? You just have spatial dimensions when you draw a parametric curve. Okay, so we're going to have we got to kind of discover here a completely new point of view on how to think about a derivative. All right, so the first thing I'm going to do is I'm going to just write down the derivative matrix. Now you'll notice that there is a single input variable. You'll also recall that derivative matrices have one column per input variable, right? Because columns correspond to input variables. So one input variable means we have one column. It also means, if you think about it, if you only have one variable, there are no other variables to hold constant. So in fact, this is not, in this case, it's not a matrix of partial derivatives. It's a matrix of good old-fashioned regular Calc 1 derivatives. Right? As you see I've drawn there, notice that those are D's, not partial symbols. Okay. Alrighty. Okay, so now I'm going to propose that this seems like a reasonable thing to write down. It is a little uncomfortable to write that down. Let me try to persuade you why this is okay. Are we sure, specifically, that a derivative of a vector is a vector of individual coordinate derivatives? I mean, we would certainly hope that would be true. That would be nice if it were true. But is it really? Right? So let me try to argue that it is. And the way forward on that, and this is, I don't want to get too lost into the weeds here, but look, we know how to take a regular old Calc 1 derivative. There it is. And notice that this process of computing a regular old derivative starts by looking at a difference of two position vectors. And now I ask rhetorically, how do we compute the difference of two position vectors? And the answer is you compute that difference one coordinate at a time. Right? That's how you add and subtract vectors, one coordinate at a time. How do you then subsequently divide by a scalar? How do we multiply or divide a vector by a scalar? Well, one coordinate at a time. Right? And now I, again, don't want to get off into fun for me, no fun for you, mathematical formalities, right? But limits, how do you compute limits? And I'm going to assert, and please trust me on this, you compute limits one coordinate at a time also. So in fact, every part of how you compute a derivative is, in fact, done one coordinate at a time. And so that's how we know this is true. Okay. All right, so the nice thing then is we have, in addition, a different way to make sense out of the idea of a derivative of a parametric curve. I can just label these players on a picture of a parametric curve and just see what it ends up being. Not that much to it, really. We have a, what you might call a starting point and then a sort of an ending point. H seconds later, perhaps, right? And then if we say, okay, well, yeah, but what's the difference of those? Okay, well, the difference is what you might call a secant vector. Y'all may recall the term secant line from single variable calculus. Well, this is a vector because it's a difference of two position vectors. Alrighty, and then we're going to take a limit as h approaches 0. So now I appeal to your sense of geometry. This line, that secant line, as h approaches 0, these points will get closer and closer, and those secant lines will become closer and closer to tangent lines. And then what that means then is that this expression here, this big expression, don't forget to divide by h, will be a vector that's closer and closer to being a tangent vector. Now, you may recall single variable calculus. If you're looking at a graph, the derivative is the slope of the tangent line. Here we have a tangent vector. And you hear the word tangent, and it kind of sounds like, yeah, it's kind of the same thing. Very much not the same thing. When you're looking at a graph, the derivative is a scalar slope. When you're looking at a parametric curve, it is not a scalar. It is a vector. It is not a slope of anything. Right? So again, make sure to keep this all distinct in your minds there. Okay, so we know the direction that this points is, this points in the direction that the curve is going. What's the magnitude of this thing? The magnitude is a limit of distance per unit time. And what is the limit of distance per unit time? Well, that's speed. Right? That's kind of the definition of instantaneous speed. So altogether then, I mean, conveniently what we have is that x prime, this derivative, right, the column vector that is the derivative matrix, it's the vector that points in the direction of motion and whose magnitude is the speed. That's exactly this old physical idea of velocity. Right? It points in the direction you're going, magnitude is the speed. That's what velocity is. So this is a lovely result, and in fact, you may even kind of remember, oh yeah, back in Calc 1, when you have a car driving along a road, right? I don't know if y'all remember, one of the models that they very often apply the idea of derivatives to is if you have a car driving along a road, and if you know the velocity is a function of time, and how do you reverse engineer the position as a function of time? And well, yeah, the velocity is the derivative of position. This is just a multivariable version of that other point of view on single variable derivatives. Now, when they talk about that stuff in a Calc 1 class, they don't talk about parametric curves most of the time. Why would you, right? It's a bit much. So they don't say it as parametric curves, but it is in fact really just this idea. Okay. All right. And of course, y'all will probably also recall that acceleration is the derivative of velocity, likewise, and that's going to allow us to answer some questions kind of like this. Now, y'all probably will recognize questions of this sort, where if you are given the velocity and a starting point, you can ask, well, what is the corresponding acceleration and what is the corresponding position? And y'all have done these kinds of questions before. These are vector-valued versions of those things you've done before, but it's morally kind of the same thing. So what is the acceleration? Well, acceleration is the derivative of velocity. And so single variable calculus. Now do recall that derivatives, as we argued, derivatives are computed one component at a time, right? One coordinate at a time. So just, single variable calculus, literally. Okay. What about position? Okay, well, let's see here. Velocity is the derivative of position. So that means position must be an antiderivative of velocity. And so as we have written here, position is an antiderivative of velocity. Again, we know what the velocity is. The velocity is given to us. We compute antiderivatives, just like we do derivatives, one coordinate at a time. Very convenient. So again, single variable calculus. Right, and I'll take this opportunity to remind y'all all that Calc 1 and Calc 2 derivative rules and antiderivative rules, all that stuff, right? That is prerequisite to this course. I'm going to assume that you're good with, I'm going to say most of that stuff. For whatever it's worth, I remember taking Calc 2 long ago, and that there were a bunch of relatively obscure formulas. I'm not going to assume that you remember every formula from Calc 2, antiderivative rules from Calc 2. But standard ones, trig functions, polynomials, exponentials, logs, the basics, yeah, absolutely. Substitutions, I assume you're good. Integration by parts, I assume that you're good, right? And just make sure you're good to go with all of that stuff. Okay. All right, now let me dispel a myth. A lot of students are somehow mistakenly under the impression that your integration constant must equal to your initial value. And that is nonsense. It is absolute nonsense. Now let me tell you where that myth comes from. Well, actually, let me tell you where that myth comes from after I show you how the correct way to compute the integration constant, and it'll make more sense in that context. So let's see the right way to compute the integration constant. We're going to look at this equation right here, and we're going to plug in t equals 0. Okay, well, when t equals 0, position is 5, 6. When t equals 0, this term, plug and chug, 3, 1. And that means that green equation turns into this, and of course there you can effortlessly solve for what c is, and there it is. C is 2, 5. Now notice, as promised, the integration constant is not equal to the initial value that's given. It's not even close. Right? Everybody see that? So where does this myth come from? And why, I've heard high school math teachers tell their students that these two things are always equal. It's nonsense. So here's where it comes from. In some high school classes, the only functions that they ever bring up are polynomials. right? And so let's imagine if this is all polynomials here. If that's all polynomials, then these are also polynomials, but where the degree is positive. Right? In other words, every single factor in those antiderivative terms, every term has a factor of t in it. And so when you plug in t equals 0, what you end up with is that this is all zeros. Right? And so you would end up with all zeros here. So because of the sloppy idea of let's just use polynomials for everything, we end up in a situation where it really does look like the integration constant and the initial value ought to have to be equal. And again, that's an illusion that results from restricting oneself arbitrarily to polynomials, which is not how the real world works. Okay. All right. So if you might have gotten out of your Calc 2 class under that mistaken impression, hopefully that's clarified at this point. By the way, don't forget as well, related point, on an exam, it's not about answers, it's about reasoning. Right? So it's not... look, it might happen. It might very well happen at some point that coincidentally, maybe the answer to the question might actually be that these might, in some coincidental situation, might actually be the same. If that happens, it doesn't matter, right? It's not a question of whether you get the right result. It's a question of whether your reasoning is valid. Right? And if you just write down your integration constant without showing a valid argument, coincidentally getting the right answer is irrelevant. Right? So do make sure that you show your reasoning. You've got to make sure in all cases that you distinguish yourself from students who don't know how stuff works. Right? So do make sure to show your reasoning. Do make sure to write down, for example, something like that. Okay. All right. Okay, moving along. All right, so last is just a quick reference. So in section 3.1, there's a bunch of stuff, quite a few pages of discussion of Kepler's work on planetary motion. It's beautiful math. And this course is chock full, and we don't have time. We don't have time for anything that's really kind of optional. And as beautiful as that work is, it's not part of the building that we're building up to, and so we just don't have time to do it. So you're not responsible for it. You may skip all of that Kepler stuff. With one exception, in that collection of pages, there is a proposition called Proposition 1.4, which basically establishes sort of a couple of what you might call product rules for single variable derivatives of vector-valued functions. And again, here you go. No big deal. That's exactly what you would hope and expect. They're easy to prove. You just write them all down in coordinates. Nothing to it. But anyway, you are responsible for this theorem. Okay. All right. Let me pause for a second. I know I go on at length. Let me give you all a chance to work in a question. Anybody? Everybody happy? Okay. All right, so moving along, chain rule. So, yeah. Y'all remember the single variable chain rule? I'm going to give you a different point of view on the single variable chain rule. Correct. I'm going to give you a specific, tailored point of view on the single variable chain rule. There are many others. They're perfectly fine, no problem. Whatever. But this point of view I'm about to show you here is going to be particularly valuable to me in adapting to the multivariable context. Y'all are going to find that I do this a lot in this course. I like to be able to take ideas that you already are familiar with and point out that multivariable, when everything lines up, how multivariable is really a lot like single variable. But sometimes, case in point here, you have to look at a particular point of view on single variable for the analogy actually to hold, for it to actually work. Right? And so the argument I'm about to show you here is for single variable, but it is just setting the stage for an analogous multivariable argument. So here we go. Now y'all will recall that one of our several points of view on a single variable derivative is that it's a relationship between input changes and output changes, or as I have it drawn here, a single variable derivative is a relationship between input velocities and output velocities. So it's what you multiply by input velocity to get output velocity. Said differently, a single variable derivative is a factor. A single variable derivative, as I'm viewing it here, is the factor that you multiply by the green velocity to get the blue velocity. Among many other points of view you could take, this is the one that I want to use here. Okay, all right, so with that in mind, let's look at a composition of functions. And there's a bunch of algebra I have written down. I frankly kind of regret writing all that algebra down. It's quite a bit of a distraction. I don't even really particularly encourage you to look at the algebra that I have written down here. Let me just do the hand-waving argument. The big idea is that if we have a function here that takes x's and gives y's, and if we compose with the next function here that takes in those y's and then spits out z's, right? Then we can ask a very reasonable question, which is, all right, well, what's the relationship between, kind of these three different velocities, right? If x is moving at a certain velocity, well, then y will be moving at a certain velocity, which means z will be moving at a certain velocity. And we're interested in the relationships between all three of these velocities. Okay, fine. Well, here's the thing. F prime is the factor that you multiply by there. G prime is the factor that you multiply by there. And the derivative of the composition is the factor that you multiply by there. And now I'm going to make what I'm going to call an arithmetic appeal. If you multiply by 4 and then subsequently multiply by 5, altogether you've multiplied by 4 times 5, haven't you? Right? I mean, so green times blue is purple. I mean, that's really going to be my argument here. Factors multiply. Right? So we can write that down. Now again, you can look at the algebra if you don't believe me. Right? But let's see here. That green factor is what you multiply by x prime to get y prime. The blue factor is what you multiply by y prime to get z prime. And altogether, that tells you what you would have to multiply by x prime to get z prime. So factors multiply. Pretty believable. And y'all will recognize, of course, that this result is our single variable chain rule, or it's one version, of our single variable chain rule that you see in a Calc 1 class. All right. Now, I know that y'all already knew the chain rule, single variable chain rule coming into this. My purpose here is not to teach you the chain rule. My purpose here is to give you a very particular angle, a very specific take on the chain rule. This take right here. All right. Now, with that in mind, you know what? Let me not get ahead of myself. I do want to make this observation. A really nice point of view on our conclusion here is that when you're talking about derivatives, if you have composed functions, the result is a product of individual derivatives. So I think a really pithy summary of what happened here is that differentiation turns compositions into products. I think that rolls off the tongue very nicely, and it's morally kind of exactly what's really happening here. Okay. Okay, so that in mind, let's think about the multivariable context. Okay, well here is a point of view that we've taken on multivariable derivatives. A multivariable derivative is a relationship between input velocities and output velocities. Specifically, a multivariable derivative is what you multiply by input velocity to get output velocity. Oh my gosh, that's exactly the point of view we had here. Single variable derivative is what you multiply by input velocity to get output velocity. It's a factor, right? Now, in the single variable case, it's a scalar factor. Sure, of course, it's a scalar factor. In this multivariable case, it's a matrix factor. A little different, I suppose, right? But it's still a factor. It's what you multiply by the one to get the other, right? So same sort of point of view there. And again, if you compose a couple of these functions, so here we go. I've got a multivariable function here that takes in an x vector and gives you a y vector, and then I'm composing that with a second multivariable function that takes in your y vector and spits out your z vector. All right, well, when you do that, you can talk about these three different velocities. The velocity of x is going to cause y to have a velocity, which is going to cause z to have a velocity. And again, we're interested in the relationships between all three of these vectors. And again, it's just kind of a matter of sort of talking through it. Let's see here. I'm going to try to remember my color choices. The factor that you multiply by x prime to get y prime, and the factor that you multiply by y prime to get z prime relate to the factor that you multiply by x prime to get z prime. And again, in the same sense that when you multiply by 4 and then multiply by 5, all together you multiply by 4 times 5. Here, same thing. When you multiply by one matrix and then subsequently multiply by another matrix, in effect, you multiply by the product of those matrices. Okay. So we get this same, we get this highly analogous result here. Let's see here. Let me get the things in the right order here. The matrix you multiply by x prime to get y prime, and then the matrix that you multiply by y prime to get z prime, all together, their product is the derivative of the composition, namely what you multiply by x prime to get z prime. So I think this is a really valuable point of view. It points out that the multivariable chain rule, by the way, notice the multivariable chain rule is a statement about derivative matrices. As it should be. Let me say it a little bit differently. The multivariable chain rule is a statement about multivariable derivatives. Remember, a derivative is a matrix. That's what it is. All right? So, yeah, of course the chain rule, the multivariable chain rule should be a statement about multivariable derivatives, aka matrices. So, so notice that this take on where the multivariable chain rule comes from is morally equivalent to the take that we used here in the single variable context for the single variable chain rule. And here we go. There it is. Now again, you can look at all that algebra if you like. I think it's arguably more trouble than it's worth. Maybe kind of a distraction from the point, really. But suit yourself. If you don't believe me, take a look at that algebra, and it all works. And again, we get this really nice punchline, which is that when you're doing differentiation, effectively what you are doing is you are turning a composition into a product. Same pithy little summary that we had for the single variable case. Differentiation turns compositions into products. Of course, matrix products because that's what these derivatives are. Okay. All right, now real quick, and then I think we're going to be out of time. You will notice that this argument that I gave you was specifically for functions of 2 input variables followed by 2, I'm going to call intermediate variables, followed by 2 sort of eventual variables. What if you have different numbers of variables? Does that change the argument? Does it change the result? And not really. It hardly changes anything at all, at least from how I've presented it here. So, for example, let's suppose that I had a third dimension there and a third dimension there. So F is 3 in, 2 out. G is 2 in, 3 out. And the composition is 3 in, 3 out, right? So this is very different situation, or so it would seem, and yet the argument doesn't change a bit, does it? It's still, we're multiplying factors. It's just that now what does change is these matrices will have different shapes, right? The matrices won't be all 2 by 2 anymore. They'll be like 3 by 2 or 2 by 3 and 3 by 2, and you gotta think through the rows and the columns. But it's still a multiplication of matrices in exactly the same way. Okay, so this works for any dimension. Doesn't matter. And I just drew it with the 2-dimensional picture just for kind of artistic convenience. And let's see here. I think that may... Wait a second. No, we have until 11:10. Oh, good. I have 4 more minutes. Okay. I got confused. I thought we were done at 11:05. Okay. All right. So let's do an example. Here's a single variable function. Here's another single variable function. I'm sorry, multivariable. Sorry. Multivariable function. Another multivariable function. And the question says, a bunch of information is given. We'll come back to that as needed. The question says, how do I find the derivative matrix of that composition? Right? So now this question, it also asks about a particular partial derivative. We'll come back to that in a second. So let's see here. We are going to just straight up use this right here. It's our multivariable chain rule. I'm just going to steal that explicitly right there. Okay, well, let's see here. I need the DF matrix at the point 1, 2. Sweet. Given. Awesome. Let's see here. I need the DG matrix at the point F of 1, 2. I'm not clear that I have that. I do have a DG matrix given to me, but I need it to be at F of 1, 2. I have it at 3, 1, 0. So conveniently, of course, F of 1, 2 is 3, 1, 0, and that means that this thing that I need is this thing that I have. Everybody on board? Okay. All right, and then it's all over with the shouting. We have these 2 matrices. We write them down. We multiply them. Boom. There's our derivative matrix of the composition. Right there. Okay. Warning. Do be careful. It is very easy to mess this up by putting the matrices in the wrong order. It is super easy to mess that up. Now, notice, you really do have to get them in the right order here. I mean, this is non-optional, right? This one has to act what you might call first. And here's why this is easy to mess up. Notice that as far as the diagram is concerned, the one that acts first is on the left. But as the algebra is written down, and as it must be, the one that acts first is on the right. Because when you multiply a matrix times a vector, you start on the right. Right, so anyway, easy to mess that up. And heads up, do be careful. You got to get that in the right order. You'll notice further in this example, and I did this on purpose, by the way, I gave you that matrix on the left, even though it's supposed to end up on the right, and I gave you this one on the right, even though it's supposed to end up on the left. Right? So it would be very easy to write them down in the wrong order. Now, in this case, of course, if you had them written down in the wrong order, you would notice that the pieces don't fit, the dimensions aren't right, you can't do the multiplication, and that might be your cue to do it the other way. That won't always be a problem. Right? There are plenty of easy examples to see that sometimes that might not be a cue that you can use. Right? So you got to make the conscious effort to think about, wait a minute, which one acts first? What does that mean about the diagram? What does that mean about the algebra? And then do the algebra accordingly and in the correct order. That makes sense to everybody? By the way, do keep in mind, why would I put these in the wrong order like this? Why am I kind of being a jerk there? No. This is an important test of, you got to keep in mind, my job is to see who, when I'm doing a test, right? My job is to see who understands the material and who's kind of transcribing, copy, pasting, doesn't really know what's going on, right? And so this is a way to distinguish knowledge from lack of knowledge. That makes it test appropriate. So heads up for that kind of thing. See y'all later. Have a good Wednesday. See you on Friday.